Good morning, I'm Manuel Tarzo. We are in Unit 8, Regression, and today in this video I will talk about problem of high collinearity in multiple linear regression. So probably the main problem in multiple linear regression is the presence of a high collinearity. I'm going to explain this problem and to provide some solutions. So imagine that I want to predict the y as a function of x1 and x2, and then imagine that both are exactly identical. Well, so if I just put one of them, x1, in the model, then if x is added, it's irrelevant, because as both are identical, so the second will not provide any further information, so the coefficient will be 0. But what happens if I make it in the opposite way? I first introduce x1 and then I add x1. So x1 in this case will be irrelevant, so the coefficient will be 0. And then what is the solution? So is it 8 that goes with x1, or is it 0 that goes with x1? Okay. Or I can, if both are identical, I can make the average of them. So the conclusion is that it's impossible to estimate regression coefficients. So actually, if I have two columns of data which are identical or which have a correlation coefficient of 1, so it means that the values are proportional, exactly proportional, okay? So if I introduce both in the regression model, I will get an error in the software, okay? The software cannot estimate regression coefficients. And then what happens if instead of being identical, they are strongly correlated? Okay, well, it could be something like this. So I have a big coefficient for x2, but a small coefficient for x1, okay, small coefficient, and then the coefficient of x1 can be small, and perhaps it cannot be statistically significant. So, and then the interpretation, it can be like a bit difficult. So we can ask, why does x1 not enter in the model if it is correlated with the y? Okay, so we can have different variables correlated with the y. So x2 is correlated with the y, it enters the model. x1 is also correlated with the y, but it does not enter in the model. It means that it is not statistically significant, and then the interpretation can be somewhat difficult, and the reason is that it does not enter in the model because it is correlated with another variable that is also inserted in the model, that is included in the model. Okay, so it does not enter, so because this effect of x1 is already explained by another variable correlated with it that is present in the model. Okay, it is the interpretation. So this is the reason. So the model becomes unstable. Unstable. What does it mean? So small changes in the model make that p-values of correlated variables undergo big differences. For example, if I discard one outlier, it can be, for example, that this coefficient becomes big and this becomes small. Or if I have like 6 variables and I just discard one which is not relevant, again, it can happen that these coefficients become like quite different. Okay, and so this is why we say that the model becomes unstable. Then it's difficult, the interpretation of the results is difficult, and then the variable selection is also difficult. It's not clear which are the variables that should be selected to be included in the model. Okay, so there are different solutions for this problem. Okay, one solution is to perform a careful selection of variables, so to decide to use x1 or x2, okay, thinking or applying like other criteria, like from a technical standpoint, which one makes more sense or something like that. Or we can use averages. So if x1 and x2 basically are measuring the same, okay, so I can make the average of both, and then I can introduce the average to reduce the measurement error. Okay, for example, imagine that x1 is one measurement and x2 is a replicate. Okay, it's like a second measurement carried with another procedure, or just with the same device but like a second measurement? Well, basically I should expect a strong correlation between them, so I can make their average to reduce the measurement error, and that makes a lot of sense. Or another solution is to use methods based on Latin structured. Okay, these methods can be applied, although we have this problem of high collinearity, and these methods are based on this idea of like averaging variables which are correlated. The methods of regression based on Latin structures, for example, PCR, which stands for principal component regression, or PLES, which stands for partial least squares regression. Okay, so now I'm going to explain a bit of the history of these new methods. Okay, historic evolution, the new area of big data. Okay, so the background of multiple linear regression is like long ago, from the gender at the beginning of the 19th century, also by Gauss, again at the beginning of the 19th century, Galton, Pearson, then in the 20th century, beginning of the 20th century. Okay, so this classical regression was like developed approximately during a century. Okay, so we can say that between 1805 and 1925, in this range of years, was the development of multiple linear regression. Okay, but a few years later, approximately 1930, we had the first calculators. Okay, so, and also as the decades progressed, the sophistication of computers and the statistical software which became available made that at the years 1960s and 1970s, there was also a development of the analytical methods of spectroscopy, chromatography, okay, different methods used in analytical chemistry. Okay, these methods have as a problem that they provide a lot of variables, which is much bigger than the number of observations. Okay, for example, we can have like the observance measured at the different wavelengths. Okay, the observance at a specific wavelength would be a variable, and we can have that observance measured at a lot of different wavelengths. So we can have this information, for example, like 20 observations. So that would be an example of that. A number of variables is much higher than the number of observations. Well, in this case, we cannot apply multiple linear regression. One condition is that the number of variables has to be less than the number of observations. Okay. Also, when we have a high number of variables, it's quite common that the presence of collinearity. So it's quite likely that we have structures or groups of variables with a high correlation. It's quite common. Well, solution. One solution is to apply what is called stepwise regression. Stepwise means multiple regression step by step. Forward means that the variables are introduced in the model one after the other, and backward is the opposite. Backward means that all variables are included in the model, and then each one is taken out one after the other. Okay, this is an automatic method of variable selection that can be very useful if the number of variables is not very high. So if we find that using stepwise regression forward and backward, if we reach the same solution with both methods, so it provides consistency and we can rely on this variable selection. Okay, but also we can use method based on Latin structure. Well, the origin was the development of principal component analysis. It's abbreviated as PCA. This method was developed by Pearson in 1901 and also further developed by Hodling 1933, and Walt, Van de Waal in the year 1964 developed an algorithmic procedure to compute PCA. Okay, well, So based on this development by Walt, there were like softwares that were able to compute principal component analysis with an algorithmic procedure, and then based on PCA we have also the regression method called principal component regression. Okay, it's a regression model, and then from the work of Walt, based on this algorithmic procedure for PCA, some years later, so we had the development of PLS regression, which is also an algorithmic procedure to compute regression. It was first developed in 1977. PLS regression, which stands for partial least squares regression. Okay, but this method had a great success in the area of instrumental analysis. Okay, what is frequently called as chemometrics. Okay, remember, in the years 60s and 70s, there was a big development of these methods with this problem, and so in this year, 1977, this PLS regression was provided, and then this method was able to solve these problems that were appearing in chemometrics. So this is why this method had a great success. Okay, and this method copes very well with the problem of high collinearity, and also with the case of missing data. Okay, so if we have some data of X and even for the Y which are missing, so that problem cannot be solved with the classical multiple regression, but it can be solved with PLS regression. And also, interestingly, it can deal with the case of several Ys. There are many software available like SimCA-P, Aspen, and Schellenberg. If you try to find in internet, so you can find different software that are able to make this regression method. So, what is the difference between multiple linear regression compared with those methods based on latent structures? Well, a multiple linear regression requires that the number of variables has to be less than the number of observations. That is a requirement. If this is not the case, the model cannot be fitted. But in the other methods like PCR or PLS, it is not required. We can use even with thousands of variables for a set of observations. Okay? Well, another condition is that MLR has some kind of hypothesis. For example, the variables have to be normal. Okay? It's based on the hypothesis of normality. So for other type of methods, this is not required, although it is desirable. Okay? So in case of using variables with a very high skewness, so it is recommended to apply some kind of transformation so that the degree of skewness is not so high. Okay. Well, in multiple regression, the model is built only with those variables which become statistically significant. Okay. So it has to be ensured that the p-values associated to the variables included in the model have to be less than alpha. Okay. But for the other models, it is not the same. The model is built with all variables, which is something interesting. This model is based on latent structure, on components, and component is a linear combination of all the variables. Okay, well, validation. Remember that I explained in a previous video that in multiple regression, validation is carried out from the p-values associated to the variables included in the model and studying the residuals. Okay. But for the other type of methods, the validation is carried out differently. It can be used in two ways: using internal validation, which is called bootstrap, with different bootstrap methods, okay, or with external validation, which means that I have the set of observations. So I take a subset which is used to fit the model, and then I use the rest of observations to validate the model as an external set for validation. Okay, this way of validation is very, very commonly used in statistics. Okay, well, as I have explained, linear regression has a problem in the case of high collinearity. But actually, methods based on latent structure, this is not a problem at all. Okay, so this is a main advantage. Again, a problem with missing values, but no, it's not a problem in these new kind of methods. So this is really an advantage. Okay, but actually there are this is another case. So in linear regression, if the variance of a variable changes, okay, the results don't change. I have the same goodness of fit, same coefficient of determination, and the p-values associated to the variables are exactly the same. So I can change the units, there's no problem. But actually, it's totally different in these new kind of methods based on Latin structures. If the variance changes, the model changes. For example, if I change the units or the scale, if I change the scale, just multiplying one variable by 100 or dividing by 100, so the model changes, and in some cases it can change a lot. So this is something that has to be taken into account. So this is like the data, there's a pre-treatment of the data before fitting the model. Okay, the variance has to be discussed, and if the variance of the variables is very different, so there is a step where all the variance is made the same, unitary variance to all the variables. Okay, perhaps this is the main drawback, perhaps. So models based on Latin structures are strongly dependent on the variance of the x. This is something very important that you should remember. Okay, important to apply an appropriate data pre-treatment. Okay, and then finally, it's always required that observations should be independent. Okay, so in case of time series, when we have that one observation is a function of the values observed before, in statistics it's called a time series, and there are a lot of methods of time series analysis that are different for these linear regression methods, which assume independence. So this method of multiple linear regression and also the others assume that an observed value of the y is not a function of the values observed in the previous instance of the time. Okay, important. Okay, so what are the kind of multivariate prediction methods that can be used? There are a lot of them. There are many methods. Probably the most famous ones are neural networks, support vector machines, which are becoming quite famous, and there are a lot of them. Well, one of the problems of many of these kind of multivariate prediction methods is that overfitting. What does it mean? Overfitting is when the goodness of fit is higher than the goodness of prediction. Okay, I'm going to explain the idea of the problem of overfitting with this case. Imagine that we have one I, which is a function of one x. Okay, and here we find a linear correlation. Okay, we have a linear correlation. What happens if I fit the y as a function of x squared, x power cubic, x power 4, the fourth, and so on? Okay, then at the end I will fit that the model fits much better to the data. Okay, so in this case the r squared is 0.86. In this case the r squared is 0.99. So this model fits better to the data. But is this model better than this one? Well, the answer is no. Okay, if I make a given value x, I cannot say that I will get a more accurate prediction with this method compared to this method. Well, this is what is the overfitting. I have used x squared, x cubic, and so on. Too many variables. Okay, too many variables in the model. I'm overfitting the model, not ensuring that the goodness of prediction is going to increase. And that is a problem. This problem of overfitting should always be avoided. Okay, so in many cases, the solution to ensure that the problem is not, the solution to ensure that a model is not overfitted is to split the set of observations into sets. A calibration set and then a validation set. Okay, So calibration set, validation set. So first, I take part of the observations, and then I fit the model, and then I calculate the variance of the residuals. Like imagine here, okay, I can compute the residuals, and then I can compute the variance of the residuals. And then for the validation set is how does the model obtained in the first part predict those observations not used to fit the model? Okay, so I can calculate those predictions and then those residuals and then compare both of them. Okay, so both variances should be similar. Like look here. Here, if I compute the residuals, okay, the residuals in absolute value will be much smaller than the residuals here in absolute value. Okay, so here the variance of the residuals will be much smaller than the variance of these residuals. Okay, this is because the model is overfitted. Okay, the model is overfitted. So in this case, so to avoid overfitting, both variances should be similar. Okay, this kind of validation is very, very common in prediction. In, I would say, many or in most type of multivariate prediction methods. But especially, like maybe like an exception, multiple linear models are not calibrated in this way. They're built with all observations and they are validated with the analysis of residuals. This is something that I have explained in a previous video. Okay, and also there are methods of cross-validation, which is like an internal validation methods, which is using all the observations. Okay, so if I have many observations, I can do that. I can split in a validation set and calibration set, but if the amount of observations is not too high, I can use all the validation, and there are softwares that use an internal method of validation based on bootstrapping or jackknifing, which is commonly called as cross-validation. And here I finished this video about the problem of high collinearity in multiple linear regression.